Mechanics. Lecture 3. Central field with potential energy inversely proportional to distance. Let us consider a special case of a central field in which the potential energy is inversely proportional to the distance from the center of the field, and therefore the force is inversely proportional to the square of the distance from the center of the field. Gravitational and electrostatic Coulomb fields belong to this type of field. Potential energy in such a field becomes infinite at the center of the field, and decreases monotonically with distance from the center of the field, tending to zero at infinity. Depending on the sign of the potential energy, such a field can be either an attractive field or a repulsive field. Section 1. Attractive field. Potential energy in the attractive field is equal to minus some constant divided by the distance. The constant depends on the magnitude of the charge of the field source and is assumed to be positive. The effective potential energy has a minimum at some distance. This distance depends on the constant included in the potential energy. The motion of a particle in an attractive field, with potential energy inversely proportional to the distance, can be either finite or infinite. The motion will be finite if the total energy of the particle is less than zero. And the motion will be infinite if the total energy of the particle is greater than zero. The equation of the trajectory obtained as a result of integrating the equations of motion has the mathematical form of the equation of a conic section with a focus at the center of the field. That is, the trajectory, depending on the total energy of the particle, can be a circle, an ellipse, a parabola, or a hyperbola. Note that in the equivalent two-body problem, the orbit of each particle is also a conic section. In this case, the focus of the conic section will be located at the center of mass of the two-particle system. Section 2. Trajectories in finite motion. In finite motion, i.e. when the total energy of the particle is less than zero, the trajectory in the attracting field is an ellipse, one of whose foci coincides with the center of the field, or a circle, with a focus in the center of the field. The lower the energy of the particle, the less elongated the ellipse, i.e. the more it approaches a circle in shape. The minimum permissible value of the total energy of the particle corresponds to the special case when the ellipse turns into a circle. Thus, in finite motion, the particle, in general, will move around the center of the field in an ellipse, sometimes approaching, at perihelion, the center of the field, sometimes moving away from it, at aphelion. And in the case of a circular trajectory, the particle will move around the center of the field, remaining at the same distance from it all the time. Section 3. Trajectories in infinite motion. In infinite motion, i.e. when the total energy of the particle is greater than or equal to zero, the trajectory is a hyperbola or parabola, the focus of which coincides with the center of the field. Thus, the particle, attracted to the center of the field from infinity, goes around the center of the field along a hyperbolic or parabolic trajectory and again goes to infinity. In this case, the lower the energy of the particle, the less wide the hyperbola is, i.e. the more it approaches a parabola in shape. The value of the total energy of the particle, equal to zero, corresponds to the special case when the hyperbola turns into a parabola. Note that the case of a parabolic trajectory physically corresponds to the particle starting its motion from a state of rest at infinity. Section 4. Repulsive field. The potential energy in a repulsive field is equal to some constant, divided by the distance. This constant, as in the case of an attractive field, depends on the magnitude of the charge of the field source and is assumed to be positive.